Yeah, thank you very much. Oh, you can clap. You can clap first. So, just a little more about myself, because I'm going to take you on a little bit of a journey here through the world of ecotoxicology and how we've, as a field of scientific researchers, have tried to look at plastics as a toxic element in the environment. So I have a background in ecotoxicology. I work with, or have worked quite a lot with chemicals in the environment and how they affect organisms like fish. And working with chemicals, we usually work with one chemical, one compound at a time, and we can kind of assume that there's some sort of homogeneous distribution in our matrix, so we know what concentration we're exposing our organisms to, and then we can start looking for effects and mechanisms of effects. And coming from there into plastics was a little bit of a shock for, I think, a lot of us that came from that background, because plastics are not one thing. Plastics are a lot of things. And we've already had a bit of an introduction there from Martin in the number of polymers and shapes and sizes that we're dealing with in the environment. And I'm going to add chemicals up on top of that. So these are really complex things that we're working with. And during my talk today, I'm going to try to give us some context and keep us in perspective, since part of our goal here really should be to look towards solutions. So I'm going to try to explain what I'm talking about and where the things that I'm talking about sort of fit into the big picture. So starting off at the beginning, or this is a couple decades after the beginning, but plastics are mass-produced and they're sold as the solution, the plastic fantastic. And I want to start by saying that plastic is a fantastic material. And we say a lot of bad things about plastics in these sorts of situations and seminars, and they are very problematic, but they also are fantastic. And plastics have, in fact, helped us solve quite a lot of problems, and a lot of the goals that we're working towards as a global community in solving, plastics have been very useful in helping us to achieve. So things like zero hunger, plastics are important in agriculture, they're important in hygiene, in food storage, and food safety. Medicine has already been mentioned. Plastics are really important in hospital situations, in a lot of equipment and materials that we're using. They're really important for reproductive health. They're important in producing clean water and delivering clean water to people around the world. And plastics are also used quite a lot as building materials. So if you look around us in this room, you'll find a lot of areas where you have evidence of plastics in fabrics and materials, in electric wiring. In most of us, I would guarantee almost everyone in this room has some plastic clothing on their bodies right now. So it's really everywhere, our entire environment, and it has been a useful material. But it's also caused problems. And we're very well aware of the fact that plastic has caused problems in the oceans. That's why we're here today. It also causes problems on land. We've finally turned around and started looking at land and looking at the kinds of problems that are there. And obviously, it's a problem with the way that we're consuming and producing, using materials in our societies. But that being said, plastic have also started causing problems back here, where plastic has solved our problems. So we're finding plastics in our food. We're finding plastics in chemicals in our medical equipment that's causing problems for like newborn infants exposed to high levels of phthalates, for example. Plastics in our drinking water. And plastic has been a big problem in terms of waste management in our cities. So it's a problem solver, but it's also causing problems. So we really have to use these materials more wisely. And again, when we're talking about plastics in the ocean, we can kind of try to frame the way we're thinking about the materials that we're looking at in terms of potential solutions, because they might be different. If we're talking about something like the pellets that Martin found a lot of on the West Coast in the report that he just told us about a few minutes ago, then maybe we have to have specific solutions addressing that industry. If we're talking about textiles, it's a completely different story. These materials, plastic fibers that we're finding pretty much in every environment on the planet right now, are problematic because the sources are so many, they're so widely spread. We're going to have to look at different ways of handling that sort of material. Up on top here, you see consumer products and packaging. So according to Plastics Europe, packaging materials are about 40% of the plastics that are produced every year go to those materials, and a lot of those are used once. So this is maybe another way that we have to think about the way that we're using materials, and if we're going to talk about solutions, we can look specifically into different industries and sectors as well. So before I move on, I need to say what plastic is, and we might hear more about whether or not I'm completely accurate here from our polymer chemist friends later on. But in terms of framing as an ecotoxicologist, what am I working with when I'm working with a plastic? Because I started off by saying that we work with one chemical at a time. And when we're working with plastics, that's never the case. Because a plastic is a polymer, so it's a complex material, and we have a lot of polymers on the market, so there's different ones. But we extract our monomers from our raw material. Most of the time that's oil or fossil fuels. And then we're using different sorts of polymerization reactions to produce our polymers, which is this chain of monomers. And that's the plastic material that we're using in our products. But in this process, Oh, here's our different monomers. And from a toxicological perspective, these monomers might be actively biologically in different ways. So polystyrene, for example, styrene monomers are thought to have some biological activity. And the same is also true for PVC. That is not this case for polyethylene or other plastics, or it's not thought to be the case. So already here we have a difference in what we're working with in terms of toxicity and biological relevance for the organisms that are being exposed. We have what we call non-intentionally added substances. So we're looking for these polymer chains. This is our plastic products. But in that plastic product, you're also going to have a number of unreacted monomers. So you have your polymer, and then you have your monomers. But you might also have some other compounds that are there from the polymerization reaction that have been added to drive that reaction. You might have some degradation products that are forming. You might have some contaminants that are coming from your raw materials, your oil, for example. So these are non-intentionally added substances, and we don't always know what these are. And we don't actually have a lot of information about what they are or how many of them there are. Then we have our chemical additives, and this is what we're putting in our products. So this is flame retardants, it's pigments, it's UV stabilizers, it could be biocides that are used in a lot of food packaging materials, it's softeners like the phthalates. And this can be somewhere between hundreds and thousands of different compounds. Again, here, a lot of knowledge gaps. I'm going to come back to this later on. But these are in our products. And then once the plastics are reaching the environment, these chemicals can leach out and other chemicals can bind onto the plastics. So a number of studies have been done looking at the kinds of chemicals you'll find in nurdles, for example, in the environment. And plastics are a matrix that do bind hydrophobic chemicals, so they can bind chemicals from the environment into the plastics. So there's my chemicals. So what we end up with is a list of different polymers. And these are the top produced ones. You recognize these symbols that you find on the bottom of consumer products, and all of these chemicals. So in society today, we probably use around 30,000 different chemical substances on a daily basis. And we don't have good numbers on how many these are, but somewhere around 30,000. Approximately 100,000 have been produced by humans in society. Theoretically, we can invent maybe 100 new chemicals an hour. Not all of these will come to market, not all of these will come to production, but this is a vast number. So we're talking about thousands and thousands of compounds. And not all of these will be problematic. Not all of these will be persistent, not all of these will have toxicity, but we don't have a lot of good information on these. So if we look into REACH, which is the European Union chemical regulation, and their dossiers where they're collecting toxicity data on chemicals used in high volumes on the European market, you'll find around 8,000 dossiers, something like that. And of those, so a German, I think a German NGO looking at chemicals evaluated all of these dossiers and found that of these 8,000 dossiers from the potentially 100,000, but say 30,000 chemicals on the market, one of them was complete and correct. So these dossiers contain the chemical toxicity information we need to assess the effects of these chemicals on human health and on the environment. So there's a big problem here in the amount of data and information that we have about the chemicals that we're using. So just to lay the sort of foundation there, this is the kind of darkness that we're fumbling around in. So now if I move on from plastic to microplastic, as we already heard, plastics, once they get out into the environment, can be different shapes. They can be films, they can be fragments, they can be irregular, they can be fibers. They can also be covered in biofilms, different kinds of proteins that are organic matter that are fastening to the particles, and you can have microbes. So what we're working with when we're working with microplastics in the environment is a really complex mixture of a lot of different things. Different sizes, different shapes, different polymers, different chemicals, different microbes, different organic material. And coming from a background where we work with one thing at a time, this kind of threw us all a little bit. How do we do this? How do we work with toxicity of this mess? So we started looking at the big plastic. And again, this was mentioned this morning, I think in our opening talk, these pictures, these charismatic megafauna, and these pictures that really tear at your heartstrings. And these pictures were probably the ones that started this whole movement and the whole public awareness of plastic pollution. So how many of you have seen pictures like this before? Probably everyone in the room. And everyone in the room knows that plastic can be damaging in the environment, that animals can fasten, they can get caught in plastic, they can become damaged, they can have injuries, they can drown. So these pictures are from what's called ghost fishing, discarded fishing nets, which are commonly found in the environment, definitely in the Arctic region, where they're one of the more common kinds of microplastic fibers that you can find in the environment. So this is a bit of storytelling. This is what plastic is doing to the environment. And I think these kinds of pictures are why we have focused on the marine environment so much, because we've seen these images. We also know that plastic is consumed by animals. And this picture is from a study that was done in the late 1950s. So we've known that birds have been eating plastic for decades, almost as long as we've known that plastic is fantastic. And this is something that we're just sort of coming to pick up now again. So Martin was talking about a study from the 1970s with plastic bags in the deep sea. And here we're talking about plastic in the guts of birds. We've known about this for a really long time. We just haven't really done anything about it. But the pictures from Midway Island, and I don't have that picture here now today, showing the albatross birds with their guts filled with plastic also, I think, sort of were one of the images or groups of images that kicked off this whole movement, this whole environmental awareness of plastics in the environment. And the artists that made those pictures did it to communicate this problem. And those birds were dying with their guts filled with plastic. One question that we haven't answered, though, is causality. And this is something that ties back to more and more evidence that's coming out today. So we see a lot of animals washing up on beaches with their guts filled with plastics, and they're dying from this. But we don't know if they're starving because they ate plastics, or if they ate plastics because they're starving. And there's more and more evidence that a lot of organisms or animals, like the puffins more recently, in the environment, and gray whales off the coast of California are suffering from malnutrition. They're not getting enough to eat. And the causality between all of these different factors is difficult for us to prove, but it's something to be aware of. But that animals are eating plastic, yes. That they're dying with their guts filled with plastic, yes. And in some cases, we can definitely demonstrate that they're being injured by the plastics that they're eating. So these things are happening. And then this last picture that I have here on megaplastic, macroplastic, this one here is from the Caribbean, where we have entire ecosystems that are filled with plastics. So this can affect the way light is moving through these systems. There's evidence that plastic can cover entire bays, so light is not reaching into the water or into the sediment areas, which can affect the way organisms are growing, algae and so on. We find plastic in the deep sea, and there is some, so Martin also talked about this, that plastic density changes over time as these materials are being fouled or there's organisms growing on them and they're sinking to the deep sea. But the plastics are also changing the rate that marine snow is sedimenting in the oceans. So marine snow is nutrient that's coming from fecal material from organisms in the upper layers of the ocean, and it sort of snows nutrients down into the deeper layers of the ocean. And these particles are changing in density because of the incorporation of plastic. So potentially, hypothetically, plastic can be changing nutrient cycling in the oceans. We don't know this yet, but there's some groups that are trying to look at this and model this. And obviously it's hard to measure on a global scale. But it's another problem that we're talking about. What are plastics doing? How are they causing harm? And then, as I said, we've recently turned around and started looking at land. So we've had our eyes on the ocean. We've been talking about microplastics in the ocean. We've been talking about plastics in the guts of whales and turtles and seabirds. But it's happening on land too. And it kind of makes sense when you think about it. That's where we live, and that's where we make all the plastic, and it's where we use most of the plastic. So the fact that it's happening on land too shouldn't be a surprise to all of us, but we haven't had a lot of scientific data or evidence of this. But animals are dying on land because of plastic ingestion. So this picture here of the deer was from the UK very recently. There was also a recent story in the United States. Deer found near a landfill with their guts filled with plastics. It's a big problem in India where cows are dying from plastic ingestion. There's evidence of camels and other animals eating plastic. So animals on land are doing this too. When we're talking about problems associated with plastics on land, some of them might be indirect. So toxicity of plastics is one thing, and I'm going to come back to that, but problems caused by plastic can be complex. So the picture over here is from a drainage ditch in Liberia, where they have a lot of rainfall. They also have very poor waste management, both when it comes to sewage and when it comes to trash and solid waste. And when plastic ends up in the ditches like this, what you get is flooding. And when in a place where you have little or no access to clean drinking water, little or no sewage management, and little or no waste management, what you get is flooding and soups, where you have human pathogens easily spread through the environment, and then you have outbreaks of pathogen-driven diarrhea, which is one of the highest killers of children around the world. And then finally, waste pickers who are exposed to excuse me, chemicals and potentially human pathogens in their daily lives and their attempts to make a living. So mismanagement of all waste, but especially medical waste and self-care products, can also increase exposure to pathogens in a lot of populations around the world. So there's a lot of people, millions of people even, that live as waste pickers, going through trash, trying to find materials that have a value that can be recycled. This is part of the wicked problem with plastic. So chemicals, and as I said, in our society are in very common use. We have a lot of them around. Pesticides is something that is also being discussed quite a lot right now. I don't know if any of you have been following the glyphosate conversations. A number of compounds have been, nicotinoids have been banned now on markets because of what they're doing to insect populations. If we're going to produce food without pesticides, a lot of farmers are turning towards what's called plasticulture and using plastic to help reduce the need for pesticides, among other things. Also, water usage is important here. But a lot of these farming practices will plow the plastic right down into the soil at the end of the growing season. And this is also something that we haven't looked at from a scientific perspective and what that's doing to the soil. So now there's a lot of studies that are going on there, what's happening there. And finally, this last picture here shows fibers and sediment in soil. So in Sweden, when we have really well-developed sewage treatment plants, we're releasing very few microplastic particles from our households and usage. We're releasing maybe 1% of what's coming into the systems. Most of the plastic is ending up in the sludge. And that was like fantastic. Look, we cleaned it all up. 99% of the plastic is gone. The outgoing water is clean, but it's in the sludge, and we put that over there on the farm. So we don't really solve problems. We just sort of move them around. So this is something else to keep in mind when we're talking about microplastics. We have very little data on the effects of microplastics in terrestrial systems either. So this is another sort of growing field where people are starting to look, what are these microplastics doing to soil qualities? What are they doing to plants? What are they doing to invertebrates living in these environments? We don't really know yet. But if I turn my view back to the oceans now and I talk about microplastics, not macroplastics, but microplastics, the small plastics, 5 millimeters and smaller, or 1 millimeter and smaller, and try to think about what they can be doing, what kinds of effects, impacts can they be having. I can divide it up into just 3 different ways of looking at it. So here I have what I call environmental vectors. So plastics can change the way chemicals are moving, potentially, in the environment. They can leach chemicals, all these chemicals that they have in the products that we have in our markets. They can sorb chemicals that are already in the environment. And they can maybe change the way nutrients are moving through water systems or through complex systems. So that's sort of the environmental matrix way of looking at it. We can look at plastics as an organismal vector. So plastics might be changing the way organisms are interacting with these compounds in their environment, how they're being exposed to chemicals or to other pathogens or to other nutrients. So how things are moving from the environment into living organisms. And finally, if the plastics are taken up into the organisms, what are they doing there? What kinds of effects are they having? So then we can look at sort of the cellular vector effect. What are the chemicals or the plastic particles doing in the organisms once they're taken up, if they're taken up? So 3 different ways of looking at this. And my area of expertise then would be on this sort of the toxicological side. What are the plastics doing? What are the particles doing? So when we start looking at experiments, so we're going to do experiments now. We're going to try to figure out what are these particles doing to the organisms? What are they doing to the oysters or to the fish or to the lugworms? We want to look at effects. But as I said, we're not working with one thing. We're working with a lot of different factors all at once. And we can divide that into 2 major ways of thinking, maybe. We can look at a particle effect or a chemical effect. So is the organism being impacted just based on the fact that it has been exposed to a particle, where size and shape and form and density maybe are important factors? Or is the organism suffering a toxic effect because of the chemicals in that particle? And I can't take these 2 apart because I can't really expose them to plastic without exposing them to chemicals. So these 2 sort of go hand in hand. So I can try to start picking this question apart by using different control factors, using other kinds of particles, or using other chemical exposure routes. When we look at experiments where people have exposed organisms to plastics, to microplastics, they do find impacts. So microplastics have been shown to affect lipid metabolism. So how fats are metabolized in the body, where they're deposited, what kinds of fats, the different composition of lipids that can be important for membrane health, for reproduction, for energy reserves. We can see effects on growth as a consequence of this. This can also be what we would call nutrition dilution, that maybe they're eating plastics in these experiments instead of food, so they're being food deprived because plastics are of low nutritional value. We can see immunotoxic effects in some cases. There have been some evidence of inflammation, of like white blood cell activation. Detoxification mechanisms have changed. So if you look in the liver of an organism, the liver is the organ that is most important for detoxifying chemicals. We can find changes there and what sorts of enzymes are working there, and what sorts of chemical systems or chemical protection systems are put in place. Hormone disruption. There's also evidence of this. And the first hormones people normally think of, if I say endocrine disruption, is reproductive hormones, so estrogens and testosterones. But this also includes hormones like growth hormone, insulin signaling factors, thyroid hormone systems, which have also been found to be affected, and neurotoxic effects, so the way neurons are signaling or growing. We've seen reproductive effects, so the number of eggs that are laying, or egg hatching, or deformation of larvae, and then behavioral changes. So how animals are moving, how they're swimming, how they're avoiding predators, how they're catching their prey. So these are all effects that have been measured in the laboratory. But when I say this, I also want to point out the fact that a lot of these studies have been done on polystyrene beads. And that's because we can buy them. We can buy polystyrene beads from producers, from chemical laboratory equipment. They're fluorescent, so we can see them, we can follow them, we know where they go. We can buy them in nano sizes. And we like to work with nanoparticles because they're more biologically relevant. And we can expose our organisms to really high concentrations of this one polymer in this one shape, in this one size, and we can look for effects. And we do find them. There are some more studies now coming out with different sizes and different polymers, but there is sort of an overweight towards polystyrene and towards beads, towards round particles, which are not very common in the environment. Most particles in the environment are irregularly shaped, and there's not as much polystyrene as there are other polymers. So this is not really representative of what you would find in the environment. Then there's also this, which we touched on a little bit when Zhao was talking. An organism in the environment will be exposed to microplastics and lots of other particles. So there's going to be organic matter, there's going to be diatoms and microalgae and bacteria, there's going to be mineral materials. Depending on what sort of environment we're talking about, you might have a high degree of turbidity, you might have a lot of organic matter in the water, and this is not always considered in experiments. So what is the relevance of a microplastic compared to 100,000 other particles? We don't really know that yet either. And there are some attempts to include this as a question or a control factor in research, and that's sort of starting to happen now, but we don't really have good answers there on how to balance those questions and weight of evidence. Is it a particle effect or not? The levels of exposure we've been working with in laboratories are also much higher than you find in the environment. So thousands of fold higher than what you would find in the environment. When we work with fish experiments, we can feed them 2,000 particles a day. But in the environment, a fish will have 6 particles in its gut. So we're many folds of change away from what we're seeing in the environment in a lot of cases. And the fact that we're working with nanoparticles in our laboratories when we really can't measure them in the environment is another issue. So there's a lot of advances going on now in terms of finding particles, analyzing them, identifying them in the environment. And there are a few evidences of nanoparticles, of plastic polymers in the natural environment, but very few. We don't know what kinds of exposure levels we're talking about at all. So we're working in the lab with things that are not really representative of what we see in the environment. Moving on to the chemical question. So, as I said, there's a lot of chemicals in plastics, both what was put in the products themselves, so the chemical additives, and which may have leached out, and then there's chemicals which have absorbed to the plastic from the environment. And the chemicals can have concentrations up to 10,000 times higher in a plastic particle than you'll find in the water. So the thinking is that if a fish eats a particle filled with chemicals, those chemicals will be delivered into the fish, so now the particle is working as a vector, collecting chemicals in the environment, carrying it into your fish, and you have an exposure. And that can happen, and there are some studies showing that that does happen. But the question of whether or not that's relevant comes up here too. There is some evidence that it doesn't happen, that the chemicals are so bound to the plastics that they're not released inside the animal. And there are even some theories that plastics maybe could clean our animals. And I don't think those studies have really shown those results. But this is a question. So can plastics clean our animals? Can they absorb chemicals from the fish into the plastic instead? So this is another issue. Yes, plastics contain a lot of chemicals. Yes, we are exposed to chemicals via plastics. But are microplastics important there? So all the chemicals in our environment are moving through the environment in a lot of different ways. They can bind to organic matter. If we take PCBs as an example, PCBs, which are now banned and have been for quite a long time, can be found in water samples in the Baltic at very low concentrations, nanogram per liter concentrations. But if you look in microalgae, and then you look in primary consumers, and then you look in snails or zooplankton, and secondary consumers like small fish, the concentrations become higher and higher through a process known as biomagnification till we reach our top predators, our seals and our birds. And there the concentrations can be so high that they cause reproductive failure. The same thing was true with DDT in the United States with bird populations. Are plastics important in how chemicals are moving through food chains? We don't really know yet. This is another question that is unanswered. So there's a lot of ongoing research trying to address all of these questions. There's a lot of questions left, and I'm sure I've missed a lot here. This is me brainstorming a little bit. So what are our uptake pathways? If an animal eats a plastic, is it taken up? If it's in the gut, as a biologist, I would say no, it has not been taken up. It's been ingested, and it can be egested. But there's no evidence that it has been taken up. So smaller particles probably can cross epithelial barriers. And there's some evidence of this from some mammalian studies. Nanoparticle-sized particles can cross barriers, but the microparticles, maybe not. Maybe they're not taken up. If an animal is injured, maybe. We don't really know. We need to look more at how chemicals and plastics are moving through food webs. Again, here there are a few studies looking at trophic transfer from algae to a zooplankton to a fish, or these sorts of systems, but we need to understand more there. Questions about microbes and pathogens, I guess, will come up a bit more with our future speakers, but this is something that we're wondering, like, is this going to be a root of toxicity, of effects that we're having in a change in gut microbiota in an organism that's consuming plastics, or are the plastics carrying the pathogens to new environments? Oh, we need to do more work on synthetic versus polymers. So is this trying to pick apart the particle effect? Is the things that we're seeing, if we're looking at the gut of a fish and we see that it's irritated, is that from the particle as such, a mechanical abrasion, or is it from the polymer? So these are more questions we need to ask. So fibers, I mentioned in the beginning, and others have mentioned them as well. We find all over our entire planet, and there's a handful of studies looking at effects of fibers, because they're really difficult to work with. They're everywhere. It's very difficult to not contaminate your system. And they're difficult to handle. And we can't buy microplastic fibers. We can buy fibers, but we can't buy microplastic fibers. We can buy microplastic beads, we can buy polymer powders, but we can't buy the fibers. The scientific community is trying to source those. How can we work with those? So there's very little data there. How plastics are affecting chemical partitioning, I talked a little bit about. The mechanisms driving the toxicity, so this would be like the molecular level stuff, like how are these changes happening in this fish? If I see a change in reproduction, why is that? And in terms of information that will drive change in society, that's maybe not a really important question to answer, but scientifically we like to understand that. We like to know what's driving the changes that we're observing. We need to identify which are the most sensitive species, which would tie back to the mechanisms. If we know the mechanisms, we can look for them in species and try to predict which ones will have higher exposure levels and which ones could potentially be affected. And then we can put all of that information into this sort of framework. So this is an image from a paper a few years ago trying to sort of synthesize the kinds of information that we're gathering. And when we're working with these questions, we want to protect our ecosystems. That's our main goal. So we want to know what's going on in the oceans, and we want to know what's going on in our bays and our sediment systems. But we don't have studies that can support that question, what's going on in our ecosystems. We have to take a step back. and look at maybe individuals or even down lower. So a lot of times we're working over here on subcellular levels, like what's going on in my organism? How is it being impacted? And I can look at a change in a protein in my fish, and I can try to draw a line from there up to an ecosystem effect. And that's really difficult for us to do. It requires a lot of knowledge and extrapolation. But we're trying to study effects of microplastics on these different levels, taking into account the polymers and the particles and the chemicals, and trying to put all of this into a framework so that we can come with information about ecosystem effects, which is what we're trying to protect. So in order to do that, we do risk assessments. And we simulate the data that we're gathering from lower levels of organization, from these cellular or individual or population level effects. And we try to look at exposure versus hazard. So the hazard is the toxicity impact that I'm measuring in the lab, and the exposure is what we know is going on in the environment. And that's the kind of data that Martin presented earlier. And we take these two numbers and compare them to one another. So we take our environmental concentration and we compare it to what's called our predicted no effect concentration. This is one way of doing this, and we can talk a lot about this later if you have more questions. But the predicted no effect concentration is essentially what's safe. What level is safe? If I know how my organisms are affected and I know what dose they're affected at, I can find a safe dose. And if my number here is greater than 1, I have a problem. Right? So this is my risk assessment. Do I have a risk? Do I not have a risk? It's kind of a black and white question. And none of these answers really are black and white, but this is trying to cook down all of this information into a black and white answer. Do I have a problem? Is there a risk in the environment? And there have been a few studies that have tried to do this. Gone through the data, taken out results from different experiments, plotted them against one another, and tried to compare my no effect concentration, my safe exposure level, with my environmental concentration. So here's a number of different species that are plotted onto what's called a species sensitivity curve, and they're using here the lowest observed effect concentration. So where's my safe level? What's the lowest exposure that gave it an effect? And they've plotted a number of different species here. You have concentration down on the x-axis, and the things they were looking at here, the endpoints they're looking at, are survival, growth, and reproduction. So in my rainbow chart there, they're sort of in the middle. We're looking at individuals and populations here. So when you get to these levels, they're a bit more unspecific, but they're also more ecologically relevant than, say, a change in a receptor protein. And they plotted all of this data together, and they compared it to what's found in the environment. And you'll notice that there's not too much overlap here. So these animals or organisms are reacting to concentrations that are much higher than what we're currently finding in the environment. That being said, Martin presented some numbers this morning that are higher than what you see on this chart. So there is maybe some risk in high-level exposure areas for sensitive species. But in general, we're a number of folds away from where we have a threat in the environment today. My clarifier. Another study did something similar and came up with these numbers. So in this study, they're using something called an assessment factor, if you see the AF there. And the assessment factor is borrowed from chemicals regulations where we try to account for uncertainty. So we take the available data that we have, we try to assess how much uncertainty we have, how much do we know, how much do we not know, where are we on understanding the complexity and finding our most sensitive species, and then we use that to account for uncertainty and try to use a safer number. So we lower our numbers here on what we can accept in the environment as safe. And here they found 540 microplastics per kilo of sediment for sediment-dwelling organisms. And there is now some evidence of areas where this number is exceeded. For pelagic organisms, 6,650. So in some hotspots, in some zones of high accumulation, we might be exceeding these numbers. There might be areas in the environment where we do have risk, but if you remember from the previous chart, probably only in very sensitive species. And to end us off, I want to tie back to the chemicals, because the question of whether or not plastics are dangerous for us comes up a lot. And there have been a number of new studies coming out in the past few weeks about how many microplastics we ingest every year, every week. And I don't know, honestly, whether or not that's a problem. We can talk about that during the panel discussion, but I just want to put this into perspective as well. So we're exposed to chemicals through everything practically in our environments, but specifically regarding plastic. So if you remember that I said that 40% of plastics are packaging materials. So this is a large volume items, and we all come into contact with them every day. My colleagues and I used all available, openly available information about the chemicals that are in plastic packaging, came up with these sorts of numbers. We could confirm use of almost 1,000 chemicals. And then we cross-checked those with toxicity databases. So this is what we know about chemical toxicity. And if you also remember, as I said earlier, there's a lot of knowledge gaps there too. We have toxicity data on a limited number of chemicals. So we cross-checked these two lists, and we came up with 148 known toxicants. And these are things that are persistent, bioaccumulative, and toxic, that are known to cause environmental damage, that are problematic for human health, or that can cause endocrine disruption. 148 in compounds in plastics that we come into contact with. This, I think, is problematic. And the lack of transparency in plastic product chains is problematic, because there's so many actors involved in these products in our societies that every person along the way loses information that came before them, and they don't transfer that information forward. So we don't really know what we're working with. We don't really know what we're exposed to. And this is a big problem for recycling, because you can't take any old plastic and turn it into any old product, because you might have any number of contaminations that could potentially be problematic in there. So this is another place where we need more knowledge and we need more transparency, what we're working with and what we're talking about. And whether or not these chemicals are affecting human health, how do we work with that? Because we don't do experiments on humans, right? We're not ethically allowed to do that. So yeah, we don't do that. But we can take samples from humans, we can take blood and urine samples, we can look at chemicals in human populations. There are a number of cohort studies looking at mothers and their children. There's a number of large-scale epidemiological studies looking at chemicals in humans, and yes, we're exposed to a lot of chemicals. And these are a number of chemicals that you commonly will find in plastic products. And yes, they're in our bodies. And then you can look at epidemiology. You can look at occurrence of different kinds of cancers, of different endocrine disorders, of different health outcomes in populations. I'm talking large scale. So thousands of people, hundreds of thousands of people in some cases, to create these databases. And then you correlate exposure to outcome. And again, this is a correlation, does not show causation. But these correlations exist, and there are connections between these chemical exposures and these health outcomes. And then based on laboratory studies, animal studies, in vitro studies, when we can understand the mechanisms, how these chemicals might drive these health outcomes, we can start to draw stronger conclusions about the exposures and the health outcomes that we're seeing in human populations. So here is a way in which plastics are problematic for human health. And we also know that if a mother is exposed while she is pregnant, her child will be exposed. If she is pregnant with a daughter, her grandchild may be exposed, because human eggs develop in utero. And there is evidence now from chemical exposures, accidental exposures, or pharmaceutical mistakes done in the 1940s and 50s, indicating that these chemical exposures can cause heritable changes over 3 to 4 generations in human populations. I'll stop there on that light note.